All right, boys and girls, this is NTI week number 3B. This is our Unit 2 Forces of Motion FRQs. So let's jump into it. This could be really bad because I have not checked the scores guide. I have no idea if these answers are right or not. Um, so bear with me. We'll see how it goes. So we have this astronaut. He's on an asteroid and he throws a rock up in the air, a distance of 2r measured from the center of the asteroid. All right. It says in here there is no atmosphere, but there is a weak gravitational field. Okay, good deal. What we got? There's a rock. Yeah, draw. Okay. Yeah, part one is to draw the relative lengths. Let me show you what I drew. This is for the rock that's being thrown right after it leaves his hand, and this is when it's at its peak. Now, if I didn't go on to part B, I would have drawn these at the same height, but I thought there was something fishy. I'm thinking to myself, why should these be the same height? We'll have to go back and look at the graphs on that, but I'm thinking there should be a difference in between the lengths of these. You should have one. The astronaut's not touching it and providing it a force, so there's only the force of gravity that's pulling it down. Let's go back and look at that. Let me talk to you what I'm thinking is going on. It says on here, this is the velocity of the rock measured from the height, like the highest point it reaches. So it's at its maximum height, it's at 0 meters a second, and then it starts increasing. The dotted line is what it should be, because if I'm in a constant acceleration, I should have a linear increase in velocity, but we don't. We have this non-linear function. It's taking longer for it to get back down. And on this one, when he throws it up an even higher height, we have a horizontal asymptote, which means the velocity is leveling off. Okay, so that tells me that since there is such a weak gravity, when he throws it up, the force of gravity at its peak is less than what it is when he first lets go. That's why it's taking longer, because gravity has less of an effect up here, and the force of gravity is making it accelerate even faster. So that's why I drew those. Let's check the scores guide. 1 point gravitational force. Okay, I've got that. Smaller magnitude when it's at 2. Okay, yeah, all right, so good. We're right on that one. So the gravity is less the farther he is away. Okay, good deal. So 2 points. Again, pause it if you need to check yours against this. Then on part B, in this, where he takes that second rock and throws it up even higher, now we have to answer these questions in paragraph form. For the first throw, make a claim about what's happening at top T. So let me show you, here's my response. According to the graph, and I did have to go back there, I wanted to make sure and be specific. On the first throw, he's reached a maximum height at T0 since it's reached a velocity of 0. Okay, so it's asking what happened at T equals 0. Since the solid line does not follow the dotted line, we can claim that the increasing r, so the height from the ground, the forces decrease, which results in a lower acceleration. So that's why the solid line does not follow the dotted line. In the second throw, I can make the claim that there is a horizontal asymptote because the rock has escaped the asteroid's gravitational field. I guess, escape the gravitational? Okay, so the gravitational field stretches on infinitely. Maybe I should have put the rock has escaped the asteroid's effective, non-negligible gravitational field, something like that. Since gravity's effect is negligible, I should put, since gravity's effect is negligible, the velocity remains constant under the absence of outside forces. Okay. Let's see. Let's check and see. I'm a little iffy on a couple things now that I've gone back and read it, but let's see. Part B. All right, so I had to answer 1 point is earned for stating that T1 is when the rock reaches its maximum height or distance from the asteroid. Yeah, I did have that. So at T1, maximum distance away, 1 statement is earned for a statement that the gravitational force gets weaker farther away from the asteroid. Did I include that? Yeah, I did say to increasing R, the force is decreased, which results in a lower acceleration. Okay, yep, I did have that, so there's a point. The weaker gravitational force means the acceleration gets smaller in magnitude, while the change in speed compared to the constant. Yeah, so it's not accelerating as much because there's less that. Okay, good. 1 point is earned for one of the following regarding the second throw. If the rock gets farther away from the asteroid, the field becomes, okay, yeah, I did put that in there. So I got that 1 point. Or you could say the rock has enough speed to escape the gravitational field, or stating the rock is far enough away from the asteroid that it moves at a nearly constant speed. Okay, good deal. Lastly, 1 point is earned for a logical, relevant, and internally consistent argument. Address the required arguments if asked. Follows the guideline. To me, it makes sense. You all might disagree, but it makes sense to me. Let's see. Oh, they got an example response. On the first throw, gravitational force exerted by the rock gets weaker, and then it accelerates in less magnitude. You can see that from the left. On the second throw, the rock is thrown farther and reaches a height where the gravitational field is negligible. Okay, that's similar to what I have. So I would probably give myself full credit. Good job, Mr. Lacey. Okay, good deal. All right, let's go on to number 2. Cover that up. All right, let's see. Number 2. Oh, I remember this fella. Describe an experiment for, okay, so you have a block on a board, and we want to find the coefficient of static friction. So part 1 is like what we've been doing in our lab books all year. You have to draw a diagram of your setup. Now, shoot, 45 minutes, I would have been pushing it because I had a lot of revisions for this one. Let me show you my first one, which I ended up scrapping. I ended up scrapping all of this. I said, okay, we're going to take some books and stack our board up on that. We'll put our block on our board, and we're going to measure how high it is. We're going to measure the angle that it's at. We're going to put a scale on here to find the mass. And I ended up scrapping first the books, and I really started scrapping when I got down here. And I'm like, man, do I really want to put all of these angles and do all this sine theta? So is there an easier way to do this? So I went back and I would have marked all of this out, and I would have redone it. So I redid my experiment for number 2. So I'm like, okay, let's think about this in a simpler way. Let's get a scale to measure the mass, which I've marked out and I'll explain later. And then I'm just going to put the board on a level table. I'm going to put my block on here. And then I'm just going to take a force sensor, which could be, our spring scale or like the Newton force spring things that we used, and a string, or it can be like a actual force sensor like what we've used with the little goobers we've got. And I am just going to diagram that out. And this is okay to do. If you add something in, if you're not sure if you need it for later, mark it out. In your lab books, I've been telling you, only include the materials that you need. So if you've got it in there, mark it out, or just erase it if you find out you don't need it. I think it actually calls for that. So here's my procedure. I'm going to put the block on the board, place the board on a flat level surface. I did have to go back and add a couple things in here for later. So I probably would have erased and rewrote this, but this was in pen. Attach a light string to the block and a force meter. So I did add my string in there. And I said hang it vertically to measure the force of gravity on the block, and then replace on the board. I would have rewrote that and made that better. Gently apply increasing horizontal force on until the block moves. I probably need to say increasing horizontal force on the block string force meter system until it moves. Record the values, and I probably should add in there of the force, values of force. And for multiple trials on different areas of the board to reduce error. So I wanted to make sure to put in how to reduce error, multiple trials, and this, we're assuming it's a uniform board, but we might want to do it on different areas of the board too. So that should be 2 parts. I have the diagram, how I'm going to do it, describe the overall procedures. Yeah, this is a biggie. This is why we want this on every lab report. Reduce experimental uncertainty and make it easy enough that another student should be able to replace it. Okay, good deal. All right, part B. This is where I had to go back and make some changes. Derive an equation for the coefficient of static friction in terms of quantities measured to produce in the procedure from part A. All right, so excuse me. Here's what I said. Here's my diagram, and I had to end up marking some things out of here too. I knew that I'm going to have this block. Gravity's pulling it down. There's a normal force up. There's a force of friction to the left and a force of acceleration to the right. And I just started writing things that I know. If I'm pulling to the right, I can get mu. Mu is going to be my static friction whenever the force applied is greater than or equal to the force of friction. So when I hit that breakover point, then it will start moving. So I'm going to look at it when the sum of the forces in the x direction is equal to 0, when the force of friction is equal to the force applied. So I know force applied is going to be equal to force of friction. This is where I started writing down some of this stuff. I know the normal force is going to be equal to mg. That's normal force is going to be equal to the force of gravity where it's level. I know that formula-wise, the force of friction is mu times the normal force. Force of friction, the normal force is mg, so mu mg. I ended up not using that because this one is asking me to solve for the coefficient. So the force of friction is going to be equal to mu, and the force normal is equal to the force of gravity. So that's why I took my string, my block, and my force meter, and I hung it vertically. I put that in my procedures to be able to get the gravitational force acting on the block. And then I know that the applied force is going to be equal to the frictional force. So mu is just going to be the frictional force, which I may need to mark that out and put force friction is equal to force applied. We'll check it and see. But the frictional force divided by the weight or the force of gravity is going, the dividing one by the other should be able to get me my mu. Now, like I said, that may come out to bite me in the end, but let's go ahead and check parts A and B. So let me screen share. Let's put that back up. Oh, please be right. Please be right. Part A. Okay, well, theirs is different than mine. Okay, that's what I had to begin with. Drawing a diagram of an experimental setup to measure the coefficient of friction that's feasible. Okay, yeah, we can do force meter, block and board. Do I have the measurements necessary? Yes, I've said I did have a scale, but I marked that out. I've got a force measure. Force sensor measures force. I think that's all I need. Third point, for indicating equipment necessary. Okay, yeah. Is this feasible? Yes. Do I have the equipment listed? Yes, I wrote the equipment and I wrote what it measures, just like we would do on our charts in our lab reports. Okay. Yep, that's good. So part 2, a description that's consistent in enough detail that another student could replicate. I think mine is simple enough. Tell me if you think differently. For a description that is conceptually valid method to find quantities, calculate. Yeah, I think mine does that too. Including a valid method for, reducing, taking multiple data points, and doing it on different parts of the board. Measure the angle between the board and the table several times. So even though mine is completely different than this one, these should be the same. So yeah, 6 points should be okay. Part B. All right, this is where I'm worried. Must be indicated. Okay, in order to get full credit all terms, all variables must be indicated in the diagram or in the procedure for part A. Oh, I don't know if I did that. For using Newton's second law. Okay, 1 point for using Newton's second law in one dimension parallel to the board's surface, either explicitly or implicitly. I did not do that. Did I? I've got Newton's second law wrote down here, but I did not do it from Newton's second law point of view in one dimension parallel to the board surface. Okay. For using Newton's second law in one dimension perpendicular to the board surface, either explicitly or implicitly. Ooh. 1 point is earned for a correct derived expression for the coefficient of static friction in current terms, part A. Okay. All right, so a couple problems I'm seeing with what I have here. I did not label my force of friction. So this, I see. So I've got force applied listed down here, but I do not have it listed up here. So that needs to be F of A. So I would not have gotten that point. I guess I need to, well, that's the only thing I need. And I guess I should have drawn, okay, so I should have taken this on here. So this would have been my force sensor.
Daddy, 2 more questions and then the first.
Okay, honey. So I should have done my force sensor with the block and indicated this was using F of G. So, okay, my bad. I should have done that. And then going on down, F of G. Yep, that I was afraid that would come bite me in the hind end. So the force of friction is going to be equal to the applied force. So that really should be F of A, because I wouldn't have gotten full credit unless I had that F of A listed in my answer up here. But since the force of friction is equal to mu F of G, that needs to be F of A, F of A, F of G. And so that means mu is going to be the applied force divided by the force of gravity. So for full credit, I should have gone into more detail, and I should have used, see, that is Newton's law. Okay. I think I would have been okay with this. It depends on how picky the readers are going to be, because I do have Newton's second law in here. I just didn't, I don't know. Maybe we'll talk about this tomorrow, see what you all think. All right, let's go on. Part C. Oh yeah, part C. Let's go back. Let's look at the question. What? Part C isn't on here. Part C, based on the data, which conclusion would the student make about the hypothesis that the coefficients of static frictions are equal? All right, so I checked that the kinetic and static frictions are not equal. Okay, so if you look at these numbers, first thing I'm looking at, this number is always lower than this one, except for here. We did this probably the first month of school. We looked at outliers. These values are wildly different than the rest. I would have kicked those out. And if you kick out the outlier, that means kinetic friction should be lower than static friction. So I put that in part C. I'm not going to go back to it because it just says that after removing the outlier, each group's values are different on average. So I don't know how many points that's worth. I'll have to look into that. That's odd. On to part D, a metal disc is glued to the top of the wood block. This was the one that I redid multiple times. The mass of the block is twice the mass of the original block. Does the coefficient of static friction move? Let me see if I can find you a table on coefficients of friction. Table coefficient. All right, see, the coefficient of friction of steel on graphites 0.1, steel on copper lead alloys 0.22, steel on copper. Okay, the value does not depend on the mass. So I know that coming in. That it's not going to depend. So like we're saying, it does not depend on the mass of these objects. It's going to be the static coefficient of friction no matter what. So I had to figure out how to put that into words. Now, when doing this, I actually misinterpreted the question the first time. I put increase because I thought they were talking about the magnitude of the friction. It's not. It's talking about the coefficient of friction. So I said the force of friction will depend on. So the more mass it is, there will be more friction, but it wants to know, does it affect the coefficient? So, okay, I had to mark that out. Then I went back and I redid it again. Remains the same. I believe that's the correct answer. And I started going back into this equation for mu mg. And I'm thinking, okay, I don't want to keep this, I don't want to add new stuff. I want to keep what I've always had before. So I marked that out. I redid it again. This is what I came up with. Remains the same. So again, this should probably be force applied instead of force of friction. But I said the force applied is going to be equal to mu times the normal force from the earlier section. So if I rearrange, mu is equal to the force applied divided by the normal force. And if the mass increases, Fn goes up, so would the frictional force of friction. Therefore, mu is independent of mass. Okay, let's see if that would get me however many points this is worth. Let's go back to that. Part D. Okay, there was only 1 point for a valid argument that indicates the coefficient of static friction is a property of the two surfaces and is consistent with the selected answer. What? Okay, so selects remain the same, referring to the equation in part B. Coefficient does not depend on mass. All right, that's what I did. I didn't want to start talking about different stuff. Okay, remains the same. The coefficient depends on the nature of the surfaces involved, not the masses or normal force. That's probably the better answer. That's probably what I should have wrote. Coefficient depends on the nature of the surfaces involved, not the masses. Normal. Okay, yeah, so it's independent of the mass. I don't get this. You could have got it right if you said decreases. The increased normal force will cause smoothing of the surfaces, decreasing the coefficient of friction. What the heck does that mean? So you could get, okay, so the way I'm reading this means you could check any one of these, but if you put your explanation of these, you would get a point. If you put decrease, but you give this explanation, you would still get a point, and increase the normal force will cause the surfaces to gouge, increasing. Okay, this is wild. Okay, so I have the right answer, remain the same for the right reason. But if you put decrease in that explanation or increase in or that explanation, you will also get credit for it too. So you can get credit for the wrong answer, even if you put that. That's wild. Take a minute, pause yours, and compare this. Boys and girls, I know this is a longer video, and this is doing something different, but I will see you on Thursday. If you have questions about any of this that's on here, please let me know, and I will score these and get these back to you. That's wild. I will check on part C for a video tomorrow, see what I can find out. Yep. Okay. Love you all. Miss you all.